So I want to talk about internal dynamics. And I'm going to start off with what is actually easier to talk about, which is Jupiter. It's actually a lot simpler than the Earth. And so what we're doing is we're adding plasma into a system. We have flux tubes, A and B, and this is spinning. Okay, so this is a rotation-driven magnetosphere. It's coupled to this spinning planet here, okay? And so the plasma gets flung out towards the furthest point along the magnetic field, number one. And secondly, if you have a lot of plasma in here, a lot of mass, then you end up with a centrifugal instability. That is, if you compare these flux tubes A and B, if A has more mass in that flux tube than B, then it'll have a stronger gravitational centrifugal potential energy. So centrifugal forces, if you like, replace gravity in this system, and you'll end up exchanging these two flux tubes. It'll spontaneously happen that these two flux tubes will interchange. This is for the case of the low beta plasma. Excuse me, if you'd like to chat, maybe you could go outside. Okay. So they will interchange spontaneously if you're loading up the flux tube A compared with that of B. So now let's think about it. If you have this as a kind of diffusion, you can think of this as a diffusive process where you have a source inside and a loss going out, then how will density vary with distance from the source? It don't need to be quantitative, just qualitatively. If you think of a diffusive process, right, and the old story was the idea of smoke in a room, and the old days of people having cigarettes, you'd think of smoke being diffused through a room, right? So in this case, we've got a source, say EO at A, filling up these flux tubes. You have an emptier flux tube B. The stuff interchanges and spreads out on very small scales. It's a small-scale interchange process. How do you see the density varying with distance from the source? Yeah. Oh, yeah. I don't think I need to repeat that comment. Okay, so how does density vary from the source? This is not a complicated question. I think you're overthinking this. Yeah. It will decrease, just qualitative here, okay? If it was moving out uniformly in a sphere, then it would be 1 over r squared, right? How will the diffusion rate depend on the gradient in density? Right? So if you have heavy concentration here, low concentration here, will you have rapid diffusion or slow diffusion? Rapid, right? So the rate of diffusion depends on the gradient of the density. Important to think about, particularly if you could imagine a steady state where you have a steady state production and it spreads out and you end up with a net gradient that is a balance between the source in here sending out stuff, flux tube interchange, some kind of it doesn't happen instantaneously. There may be processes that sort of resist this interchange at the ends of the flux tubes. And so there will be a balance between this outward transport rate and developing a gradient. But then if you increase the source suddenly, EO starts spewing out more material, then you would steepen the gradient and you would end up with more rapid transport. Okay, so let's think of another situation of the specific situation here where we have Saturn, we have Enceladus, we have stuff being transported. And it'll go out faster than inward because, of course, if you think of the interchange in this rotating system, then the centrifugal potential, you're going to be thinking of it as it'll want to flow outwards, if you like that. It's a bit like wanting to flow down a hill. The flowing down a hill in the case of centrifugal potential is for material to go out rather than to go inwards. And so it's harder for material to go inwards. You end up with a steeper gradient and faster outward transport and a less steep gradient in flux tube content. This NL squared is flux tube content, the total flux content on the flux tube. Okay, so let's think a bit about plasmaspheres. These are the sphere of plasma that's generated inside, dominated by rotation. And for the Earth, we have a plasmasphere that's quite closely confined to the planet. It's viewed here in a helium emission, but you can see there's this region around the planet that is dominated by internal sources, and the material is rotating with the slowly rotating Earth. Out at Jupiter, we have a large disk of plasma that is material moving away from Io outwards over periods of tens of days, and as it goes out, it heats up. Now, wait a minute, you may be saying, okay, but you're expanding from a small volume into a larger volume. Most gases cool off as they expand, right, into a larger volume. But in this case, the plasma heats up, and it moves from a few 100 eV up to tens of keV, and so the beta actually becomes much greater than 1, tens to 100. Where does this energy come from? Where do you think the energy could come? What are the potential places that the energy to heat this plasma could come from? Make a wild guess. Magnetic fields. You're not actually reconnecting fields, so you're not actually converting magnetic field energy into particle energy like you do with reconnection. Remember that discussion about reconnection and the circles and so on. You're coupling with the magnetic field, though, to the planet. Yes? Exactly. Angular momentum of the planet. You've got this huge flywheel in here coupled to the plasma by the magnetic field. So how does this work? Well, we've been waving our arms about how to do this, but Marissa Vogt did a PhD with Margie Kivelson, finished up last year, and she did a very nice study where she took a flux tube, and on the dusk side, as the flux tubes come around, they expand outwards. They're compressed on the day side, and as they go around to the dusk, they expand. And it was pointed out a long time ago by Margie and others that if it expands rapidly, you could violate the second adiabatic invariant. Do you remember the second one? The bounce one, right? And so if you think about it, this is a very large volume here, and that if you stretch out the flux tube faster than the bounce period, then you can actually gain energy. And it's in fact gaining centrifugal potential energy as it goes out. And so the net result is, and I'll just show you this, the bounce average energy is this blue one. You have an increase with time, whereas if you don't have this non-adiabatic behavior, it decreases with time. So this is just a first study. There's a lot more interesting things to be done here, but this is the beginning of solving this big mystery as to why the magnetosphere of Jupiter is so hot. There's also pointed out that once you start to have hot plasma, high beta plasma, you actually get the ballooning instability that enhances the outward transport. The transport goes faster, but I won't go into this. Okay, so let's think about the Earth. Earth is more complicated than Jupiter. You don't just have simple rotation coupling to a rotating planet. What we have here is the coupling to the solar wind. And the process whereby we couple to the solar wind is indeed through magnetic reconnection. Let me just point out for scale, we have the Van Allen belts here, and then we have the plasmasphere. So the plasmasphere is the rotating part, and then the rest is the stuff that's dominated by solar wind interaction with the magnetosphere. So you've probably heard of the Dungey cycle, this cartoon that was drawn on a napkin in Paris in 1952, or whenever it was, 1961. Very romantic. He was sitting there at a cafe and had this idea, how can I explain the magnetosphere? And he drew this cartoon. And what we have is solar wind coming in, convecting the solar magnetic flux, and under certain conditions, you would have oppositely directed field. In fact, nearly always, there's somewhere on the magnetopores where there's a substantial component of the magnetic field oppositely directed to the internal field. You have reconnection. The flux tubes get carried. So you have reconnection happening here. You have flux tubes carried over the pole, down towards the tail. You have stuff driven towards the equator. Reconnection on the tail. Flux tubes coming back, cycling through to the front of the magnetosphere, more reconnection, and so on. So you have this cycle of opening and then closing in the tail, reconnection that drives this process in the magnetosphere. If we look in the equator, you are getting, this is the X line where you have the tail reconnection, you have a return flow in the equator of material, bringing not only plasma back through the magnetosphere, but also returning the flux that was closed back here. So there's variable opening and closing rates. These are not equal. You know, you do the Dungey dance like this, open it up, close it down, you know, and you make it look like it's all very systematic, but in fact, there's a lot of opening, and then it builds up, builds up, builds up, builds up, and then crash, it closes on the tail. So they're not equal. Though on average, over time, obviously there has to be equal opening and closing to conserve magnetic flux. So reconnection, Thomas Gamboshi talked a bit about this, the MMS mission that will be launched in 2015 will solve the problem of reconnection. They always say that, right, don't they? Each time they do a new mission, they're going to solve the problem. They probably won't, but they'll move things forward, one hopes, in understanding what's going on, where you have multiple scales. You have a larger ion scale, which doesn't show up in this diagram, and then a smaller electron scale. And the big debate is, how does the process, what triggers the process, what makes it work? But we know it happens. We have good evidence of it happening. The devil, of course, is in the details. So what's happening here? We have this Dungey opening and closing, looking at a side view, but it's important to think about this polar view. And in fact, I confirmed with Margie that Jim Dungey had this picture in mind of the ionosphere and thinking about what could be driving polar flows over the top and the necessary return flows on the side. And really, one way to think about it is the return flow here is somewhat driven by the fact that you have to have, the ionosphere is incompressible and you have to have a return flow. And Margie demonstrated this at tea yesterday. She took her cup of coffee. She always has a cup of coffee with her, like I tend to too. And she put her finger in it and she said, look, Jim Dungey would do this in Paris, 1960, at a nice cafe. Imagine. You pull your finger one way and you see the return flow, right? This is incompressible fluid. You pull it back, you see the return flow, okay? Especially if you have a scum of milk on the top. So this was known. It was observed in the ionosphere from radio observations of the ionosphere, and this is evidence of this system going on out in the magnetosphere. Of course, the details are all in the ionosphere-magnetosphere coupling, and the ionospheric-magnetospheric coupling part is the important part of it. Luke and Rod will talk about this. Yes? Right. Indeed. So, yes, you will be addressing why. I mean, wait a minute. How could the ionosphere be incompressible? It's a gas. Should be fine. Should be compressible. You will talk why it's incompressible. Thank you very much. Brilliant. Okay, so I'm going to talk a little bit about how this system is driven and the scaling systems that we use for solar wind, the Dungey cycle. And I'm going to give the conventional, what's called the EJ approach, electric field current approach. Huge arguments. People like Gene Parker and Vytenis Vassiliounis, the big grandparents of our field, grandfathers of our field, are pushing for a BV, a magnetic field and flow approach. I have yet to find one in a textbook. I'm going to use the standard one, but keep in mind that there's some debate about taking this approach. So let's think of this system, the Dungey flow, the return flow here, and you can think of this in terms of an electric field, a convection electric field. Strictly it's advection rather than convection, but that's beside the point. So you have a flow that is associated with electric field, and you have an electric field that goes across the tail, and we can write that in terms of the solar wind and the magnetic field and some efficiency. And this efficiency factor is somewhere between 10 and 20%. And so if you think of it out here, you've got B like this, V like this, and you have an E like this, okay? And you look at it, the approximation, which is pretty crude, is that this constant across the magnetosphere, so you have E like this, B like this, and V like this. So this flow, one way of describing this return flow in the equator is in terms of this flow driven by a global electric field that is produced due to the reconnection cycle. This is the fairly standard description of how it works. So you then end up with a flow in the magnetosphere that you can write in terms of this reconnection efficiency, a V solar wind. And if you have a dipole field, then you can scale things in the magnetosphere this way as 1 over r cubed, normalized to the magnetopause distance. So you'll see why I've normalized it that way in a minute. So what's happening throughout this process is that you've got kinetic energy being built up, converted to, from the solar wind, driving the magnetic energy. You're storing it in the tail in this growth phase. You open, store in the tail. And then at some point, the triggering point, and that is the big question, is how it gets triggered. You have a substorm effect, reconnection occurring in the tail, and this magnetic energy that was stored in the tail is converted to heat, and kinetic energy flows, and particles are accelerated and produce the storm aurora. So these phases are energy storage, energy onset, and then recovery. And these locations where this happens is described as the neutral lines. There's nothing neutral about it. It's full of charged particles, but for some reason people call these neutral lines where this occurs. So the aurora is associated with this process, and energy is transferred into the atmosphere that way. Okay, the reality is messy, and there are lots of models, and in fact you'll probably be playing around with some of them in your labs that try to simulate this more effectively. And of course the dynamics are exciting in terms of space weather, about which you've heard a fair amount already. So I want to bring these two together now, the rotation of the internal magnetic field, the Dungey cycle associated with solar-driven flows, and let's see when and which dominates over the other. So we've got a co-rotational flow in the magnetosphere going around like this, and this is where you're coupling the plasma in the magnetosphere to this rotating planet in the ionosphere. And so you can compare this co-rotational flow to the convective flow associated with the Dungey cycle. So we have the convection flow associated with the solar wind and a reconnection efficiency. Now what you can do is derive the distance at which the solar wind-driven Dungey cycle overwhelms the rotation-driven internal flow. And you can do this by saying, at what R do these two flows equate? That's just algebra. You say these two are the same, and let's find out what fraction of the planetary magnetosphere is rotation-dominated. What fraction of the magnetosphere is plasmasphere? We're describing plasmasphere as being the region where stuff's going around coupled to the planet's rotation. You do this algebra, and what you end up with as an expression is that the magnetopore's distance normalized to the subsolar magnetopore's distance can be written as something that is basically scales with the rotation rate and 1 over the solar wind speed, reconnection rate in here, all inside this square root. Or you can rewrite it, since your magnetopore's distance we derive from the Chapman-Ferraro distance, you can rewrite that in terms of the planetary magnetic moment and the solar wind density and so on. So let's think about this, and I want to use this formulation. The magnetopore is divided by the plasma pore is divided by the magnetopore's distance. And I want you to think about what would happen, how would the location of the magnetopores change if reconnection was more or less efficient? Say it's more efficient, what will happen to this distance to the magnetopores? You've got really strong reconnection occurring. What's going to happen to that magnetopores? Will it get smaller or bigger? It'll get smaller, right? Rotation will only dominate in a small region, and that Dungey cycle convection will dominate over a larger region. Okay, what will happen if the planet spins very slowly? Look at this term here. Omega is the spin rate. It's on the top. So that if it spins fast, your magnetopores will, your plasmasphere, your plasmapores will go out. Okay? Makes sense. You can also think about it also, you'd have to think about the magnetic field strength. If the magnetic field of the planet is really strong, then actually you'll end up pushing that magnetopores, that plasmapores out, as well as the magnetopores out. Okay, but let's look at this. The case of the Earth, Jupiter and Saturn, we plug that formula in, and what you find is that the Earth, the plasmapores, is indeed a fraction. This is a little large. We just put canonical numbers in. More realistically, it's more like 4 Earth radii, 4 to 6 somewhere. It's actually very variable. At Jupiter, if you put the numbers in, you end up with a number that it's 350 planetary radii, which would be way outside the magnetosphere. So this is a very heavily dominated, rotation-dominated magnetosphere. And for Saturn, you get something which is also rotation-dominated, but maybe a little less so than it is for Jupiter. So there are some assumptions here. We're just assuming that reconnection, the Dungey cycle, large-scale steady-state reconnection, drives this interaction with the solar wind. And we're assuming that the planet is rigidly coupled to the magnetosphere through magnetospheric currents. Okay, so let's look at some examples of aurora that are at Jupiter, which are manifestations of what's going on in the magnetosphere. We have 3 kinds of aurora. We'll have a main auroral oval, which is pretty steady. I'll show you movies of this. We have aurora associated with moons, and Margie will talk a lot more about this on Monday. And then we have some variable aurora in the polar regions. So this is a movie where we've moved into the rotating frame of Jupiter. So this is fixed magnetic coordinates. And of course, Jupiter spins every 10 hours. So relative to the Hubble that was making these images, you see this variation here, this thing rotating around. But if you look carefully, you can sort of see there's a main auroral oval that is pretty steady. There's some twinkly stuff in the middle. And then over here, you can see this is the Io footprint that's moving around, this sort of wake of Io. There's another little dot associated with the other moons. Okay, so this is very different from the Earth's aurora. This main auroral oval, when we average it, is very steady. It's very little variation. It's about 1 degree narrow and not a lot of variation. Barely changes with solar wind. Barely changes with the solar wind. Pretty constant. There is also a magnetic anomaly we have up here, a bit like the South Atlantic anomaly for the Earth. So a non-dipolar component to the magnetic field. And the North Pole is way offset from the rotation pole compared with the South Pole. Okay, like the Earth. Does anybody see the new press release about the Earth's North Pole charging across towards Russia? Right, it was a cool. It's not a new result. It's been around for a while, but it's hit the news. Emerged yesterday in the news. Yes. Compared with the others, it's weak in terms of total emitted photons. But if you look at the per unit area, it's comparable. Yeah, there's a lot. These are million amp currents that are flowing from Io to the planet. Yeah. Yes. So what's happening here is we're coupling the plasma to a flywheel, which is the planet. But at some point, the plasma that's moving outwards, okay, so it's moving out through flux tube interchange, this diffusive process, but it's still coupled to the planet. And so momentum it will want to slow down, just as the skater slows down when he puts her arms out, but it's coupled to a rotating object, so it'll want to spin it up faster. And so what happens is you end up with, you pull back the magnetic field because it's slightly subco-rotating. You generate a curl of B, this is a radial current, and then you have a radial current, a J cross B, that enforces rotation. So the point is that if it's purely co-rotating, it just keeps co-rotating and it's coupled perfectly to the planet, but at some point it begins to slow down from rigid co-rotation. It's no longer perfectly coupled. These field-aligned currents try and couple this plasma to the spin, but at some point that breaks down. And so as this plasma that's produced here is moving out, you end up with driving these field-aligned currents, and things begin to break down because there are difficulties with driving these currents. Now, why are there difficulties? Well, part of the problem is the plasma is confined to the equator. There's very little plasma up here, and so you have a hard time carrying those currents. There aren't enough particles to carry the currents. And with most plasmas, when that happens, you develop a potential drop, a double layer, which accelerates the particles to allow you to keep driving the current. That's how plasmas work. But it's not clear exactly that this actually happens and where this happens. This happens with the Earth's auroral region. We suspect it happens at Jupiter, but we've never been there, so we don't know for sure. The real question is, where is the clutch slipping? Where is the slipping between the mass out here that is increasingly loading on the planet's rotation? Where does it break down? Does it break down because this gas planet isn't coupling momentum from the interior spin out to the atmosphere and ionosphere? So does it break down in the atmosphere? Does it break down in the neutral ion coupling, which Rod will talk a lot more in Luke 2, that coupling between ions and neutrals in the ionosphere? Or is it a lack of current carriers at high latitude. And you can think of the development of small-scale paraelectric fields as a way of decoupling the plasma out here from the rotation of the planet. The field lines just slip across on top of each other like this. Okay. Okay, so think about this. What if you had strong thermospheric winds that drive a circulation in the ionosphere? What might be the manifestation in the magnetosphere? We'll be thinking a lot more about this later. Let me give you a hint what I'm thinking about. Think of a very symmetric magnetosphere like Saturn. Very symmetric magnetosphere. And then something in the winds in the ionosphere are driving the ionosphere that sends currents out into the magnetosphere. So there's been this mystery that Saturn, remember that Sabina talked a lot about the magnetic field being very tightly confined to the rotation axis, very symmetric magnetic field, and yet when we look at Saturn, we see huge asymmetries in the behavior of the magnetosphere. Something must be driving those asymmetries. And one way in which you could be doing this, and this is recent work by Jean Gigia, Margie Gibbelson, and Tomasz Gamboshi, if you have a vortex in the ionosphere, you could produce asymmetries in an otherwise symmetric magnetic field. Asymmetries in the magnetic field driving currents that are driven from the ionosphere to the magnetosphere. So this is a way in which ionosphere-magnetosphere coupling could lead to distortions in the otherwise very regular magnetosphere of Saturn. Okay, so more about this in future lectures. So let me, I want to finish up with talking a little bit now about what we think is really going on in the rest of the magnetosphere and what is the role of the solar wind in driving this giant beast. So we've talked about this problem of coupling this mass flux here to the planet, potential ways of breaking down this coupling, particularly paraelectric fields. There's also a problem that the alphane travel time between the equator and the planet gets longer and longer as you move out into this distant magnetosphere. There are also factors in the thermosphere and ionosphere coupling. At some point, it's no longer able to drive enough currents to keep everything coupled. And so basically what happens is a decoupling process. Communication between the planet and the magnetosphere sort of begins to break down, which is where we begin to see that main auroral oval. So that main auroral oval is not associated with the Dungey cycle. It's associated with the breaking down of coupling between the stuff from Io moving out in the magnetosphere and the planet. And then they actually begin to stop talking to each other once you get to about 60 RJ. So what actually happens to the mass that comes from Io? Well, it goes around and around and around many times. Remember, it takes about several weeks to move out, so it goes round about a few dozen times. And then eventually what happens is the magnetic field, you're loading it up with hot plasma, it stretches out, and you spontaneously generate, you have reconnection here, but not driven by the solar wind, but driven by the fact that you're loading up these flux tubes and you'll begin to send plasmoids down the tail. Same sort of process as Earth, but it's not driven by the solar wind, it's driven by the fact that you've got flux tubes that are laden with plasma, hot, heavy plasma. And indeed, if we use observations taken by Galileo in the tail, again by Marissa Voigt, there's an X line across the tail that we see. It's not perpendicular, but at an angle, and we know that there are plasmoids that get ejected down the tail. So I want to come back to the fundamentals of this coupling system. We've talked about coupling between the magnetosphere and the ionosphere. That's the rotating plasmasphere. We've talked about Dungey circulation, which is really coupling between the ionosphere and the solar wind. But there's also an interaction that could happen between the solar wind and the magnetosphere, the outer layers of the magnetosphere, which we could describe as a viscous interaction. And I'll tell you a little bit about how this works. So it's been known for some time that if you think about the solar wind and then going through the bow shock, becoming a sheath of flow that goes around this obstacle of the magnetosphere, that you end up with a shear, a velocity shear between the outside sheath flow and the interior plasma. And when you get a shear in flow, you tend to get this Kelvin-Helmholtz instability. And particularly, it's been proposed that this happens on the flanks near the equator, that you would get this instability occurring. Could these processes on the boundary in a collisionless plasma, we're not talking collisions here, we're talking small-scale instabilities, plasma instabilities, could that act like a viscosity? And indeed, the simulations looking at interaction, this is current, this is electric field, this is velocity, having this shear. And this is a cartoon that we call a candy wrapper, or sweetie wrapper if you're English, with this idea of the magnetosheath magnetic field, which is red, and the internal field, which is black, having small-scale reconnections. So you can see reconnection here, where you have interchange of material and momentum between the outside flowing plasma and the inside magnetospheric plasma. Now, this is thought to be maybe relevant to the Earth when the field is not oppositely directed and driving a strong reconnection at the Earth, but is probably, we think, very important at the giant planets. And Peter Delamere has been doing these hybrid code simulations, particularly when you have heavy ions on the inside, light ions on the outside. You can drive these vortices that will lead to extraction of momentum from the solar wind and material being mixed between the outer layers of the magnetosphere. So again, arguing that small-scale, intermittent, turbulent, nonlinear processes, reconnection on a small scale, could act a bit like viscosity. So what the picture that we have in the case of Jupiter, and I take Jupiter as the extreme opposite end to the Earth. Of course, there could be things in between. Saturn is very much an in-between case. But we have to think about what could happen if we had these stresses on the outside. So let's combine our rotation-driven interior with what could be happening on the outside. So you have this interior plasma disk. You have a tail reconnection, variable in space, probably small-scale blobs rather than the entire X-line going unstable. So stuff getting sent down the tail in small plasmoids. Then let's think about, we've got observations that show this happens here. The big question comes, what's going on the flanks? And unfortunately, we've not sent a spacecraft down here, so we can fantasize and do whatever we want. We can think. We're not constrained by data yet. But I was inspired by this simulation that Jean Gigier, working with Tomasz Gambosi, with Bats R Us, looking at Saturn, produced, because of the interaction on the boundary, produced what I call a wing, you could call it a chicken wing on the side, of closed flux here, where there's an interaction between, I think, the boundary here, the sheath that's going around, and the closed flux that's inside that leads to this chicken wing, or this wing of closed material here. So this is the picture we have, rotation inside, plasmoids going down, and then momentum being transferred from the magnetosheath into the magnetosphere. We have this region of closed flux here, maybe. We have small-scale material being sent down the tail, little blobs of material, maybe reconnection of plasmoids happening here. But the real question is, this is a view that's looking down at the equator, which is where most of our observations are. What is the corresponding view of what's happening at high latitudes? We know the draped field tends to be perpendicular and go over the top. How big is the polar cap? What is the configuration up here? How important, if any, is a large-scale Dungey cycle carrying flux over the top, building it up in the tail? Is it important at all? We don't know. Yes?
Right at the edges where the ionosphere fit, what exactly is the direction of the
Okay, so think of the spiral of the Parker spiral. So at Earth, what is the angle of the average solar wind coming in towards the Earth? What's that angle? 45 degrees. Any advance on 45? It's about 45 degrees. By the time you get out to Jupiter, it's basically 90. So it's either this or it's this, one or the other. We've got a little bit of wiggling around, but it's perpendicular. Right. Okay. So indeed, that's important, and a student, Mariel de Roche, worked with Peter Delamere and I and did a study of that, and we find that the Kelvin-Helmholtz is most unstable on the dusk side, just as it's coming around. Indeed, we've looked at that. That's a good point. It is stabilized in some places. Yeah, good. But then there are also other modes, right? There are always more modes. When you go down to smaller scales, there's always something operating. Okay, good point. But the point I want to make here is this polar cap region is where we will fly with Juno. Juno will go in there and fly over the poles and tell us that we are totally wrong. Hopefully not. Okay, so the point is that I actually think that the magnetosphere of Jupiter is more like a colossal comet than it is, in fact, an Earth-like magnetosphere. And we have to think of the solar wind being hung up on the boundary layers in this viscous interaction. With a comet, it's the pickup process, the ionization of the neutrals coming from the comet. In the case of Jupiter, it's this interaction between the magnetosphere and the outside solar wind. You have an internal driver of material from the eoplasma, send stuff down the tail. And I do believe that, in fact, the tail configuration could, in fact, be more like a cometary or Venus-like interaction than the standard terrestrial magnetosphere. Juno will go there, gets there 2 years' time, will fly over the poles, measure what kind of polar auroral processes there are, the double layers like there are at Earth. We'll have observations of the aurora, we'll measure the particle fluxes, we'll measure the field, and we'll really work out what's going on at the poles. Finally, 5 minutes, we have Uranus and Neptune. Uranus, this is the time of Voyager. The spin axis was pointed towards the sun, the Earth, and the axis, we've got this big angle, this big tilt of the dipole. It's not strictly a dipole, but it's good enough for this purposes. And you can see, just half a rotation later, you've got quite a big change in the configuration. This plasma sheet in the tail is going to flap up and down with the rotation. And this is a simple simulation showing that as the planet spins around, this flapping will propagate down the tail. At what speed will perturbations in the magnetic field, this flapping of the sheet, move down the tail? What plasma speed, what speed do perturbations in magnetic fields move? Alpha in speed. So moving at the alpha in speed down the tail will be this perturbation. And so you end up with this wrapped up plasma sheet. Very different configuration to anything we have at Earth. But then you have to think, well, wait a minute. What will the configuration be quarter of an orbit later around the sun when this spin axis is no longer pointed towards the sun. So if the sun's there and it's spinning around this way, quarter of rotation later, it'll be spinning around this way with the field going around like this relative to the sun here. Can you imagine what that looks like? It's a little bit of a mind bend to try and work out how that would work. But of course, we haven't been there. We weren't there when that happened. Neptune, we have a situation where the tilt is a bit like the Earth, 20-something degrees from the orbital plane, but the magnetic field is heavily tilted, not twisted, heavily tilted with respect to the spin axis. So here is the configuration at one point, very much like a terrestrial magnetosphere, all very familiar. But half a rotation later, you've got the magnetic axis pointed noon, midnight. Weird. So you end up with a plasma sheet that's actually cylindrical. Half a rotation later. Totally weird. So this is very strange. And it's very hard to imagine that you could actually trap any plasma in such a magnetosphere, right? Heavily dynamic, constantly changing. Rotation rates are sort of 15 hours or so. I forget the exact number. So these are very interesting magnetospheres. We got one flyby of each by Voyager. We're celebrating the 25th anniversary of the flyby of Neptune on the 25th of September this year. So 25 years ago, that was it. Done. So we should really go back to these places. I want to leave you with this one slide, which is my sort of summary of what I see the principles of thinking about coupling between the three components, the ionosphere, about which you will hear a lot more, the magnetosphere, and the solar wind, and that this ionosphere-magnetosphere coupling is very much this idea of the rotating plasmasphere. But then what happens at the boundary? Do you drive any substantial Dungey circulation coupling the solar wind to the ionosphere, or are you coupling the solar wind to the outer magnetosphere in this viscous interaction? So I want you to think about, when you look at extrasolar planets, when you think about whatever objects you're interested in, how do the internal properties control the magnetosphere? And when I say internal properties, what am I talking about? What could be typical internal properties of a magnetosphere that might be important in magnetospheric processes? Plasma content, big strong sources like a moon, right? Or an outflow from the ionosphere, you could imagine. What else? Rotation of the planet, indeed, right. What else? The magnetic field, how strong it is, but also whether it's dipolar, whether it's tilted, whether it's non-dipolar, high non-dipolar components to the magnetic field, whether it's about to flip or is flipping. We've never really worked on those. What else is another absolutely key, about which you will hear a lot soon? What's the next thing on the agenda? Ionosphere, very important. Okay, do a mind experiment. What would happen if your magnetosphere, if your planet was a pure insulator? A dynamo inside a region that is thick rock, let's say ceramic. Let's make it really an insulator, electrical insulator. What would the magnetosphere look like? What if your planet was a perfectly conducting metal ball? No ionosphere, but a perfectly conducting magnetic metal ball. What if you had a neutral atmosphere, but no ions? I think that never happens, but one could imagine a fantasy world. What if you had just ions and no atmosphere? These are all really exotic beasts, but I'll bet you there's some extrasolar planets that have pretty much any of these properties, right? So it's important to start thinking about how these things would work. And it's an important sense of getting how the relative importance of these things are. External properties, what are the external properties? Solar wind, the stellar wind. Sorry? In the magnetic field, right. What is the control of the magnetic field? Magnetic field and wind conditions are basically, but it's orientation of the magnetic field that's important, right? The wind is pretty much all going out. UV flux, did someone say? Did I hear? Yeah, UV flux, very important. Ionizing radiation. Yeah, good. Okay, great. I think we're done. Thank you very much. And no, I didn't forget my homework. I do have some, I hope, relatively easy questions, which I will put out at the back. We're technically supposed to discuss on Monday. Okay, yes.
So let's assume that we're not going back to.
Oh!
What remote diagnostics?
Oh, excellent question. Very good question. Remote diagnostics. Okay, those exoplanet people, what do you think the remote diagnostics could be? What do we have? How did we detect Jupiter back in 1959? Radio, right? Radio emission is probably the best way. And there isn't just synchrotron emission, there's also radio associated with the aurora. Strong radio emissions associated with the aurora.
Particularly for these weird.
Yeah. Okay, there's a cutoff to the frequency, the highest frequency that you can observe. At Jupiter, it's about 40 megahertz. It's actually 39 megahertz. And that's because of the surface field, the strength. So the highest frequency that you can have is associated with the gyro motion at that strong field. So the cutoff tells you the strength of the field. After the fact, yes. But we knew long before Voyager or even Pioneer got there, we knew that from remote observations back in the 50s for Jupiter, right? But for Uranus and Neptune, it's harder. You can detect them, but not from Earth. You sort of have to get out there a bit. It's a good question whether or not Ulysses has actually detected them. It's hard. So you can look with Hubble, and you can look in the UV, and you can look in the optical. There is a paper that was in Science or Nature. I was a referee, I will be quite honest with you. That was very sketchy detection of aurora at Uranus. Now, they're pushing for a mission in Europe to Uranus. And even though I didn't really believe the data, I said, yeah, go ahead, publish, because I thought, this is good news. And I think all news is good news, even if it isn't quite accurate or believable. But it was sufficiently believable that it was worth publishing. So, sorry? That's exploration. Yep. Yes, exactly. No harm in it. So you can look at the UV observations, you can look at optical, look at clouds. Clouds don't really tell you a whole lot, but magnetic, it's tough. It's really, really, really tough because you want to get up close and see it. And it's hard to do that unless you have a spacecraft. Yeah, it's hard to do remotely.
Okay, let's take a break.
Okay, we can talk about that later.